So, kinematics. What do you suppose the most important concepts in kinematics? What were some things that were big? Came up on the exam maybe more than once, or were worth big marks? Maybe some of those things got used in more than one unit.
Vector diagrams?
Yeah, vector addition. That's definitely a big one. Okay, vector addition was big. We used it in Unit 1 and in Unit 2. Since I used it in 2 units, is it possible that that could be one of the questions I talked about the other day that involves overlap of concepts from 2 units? Okay, I mean, we could have one of those vector sum of all forces Newton's second law questions that would involve you having to use vector addition to get the net force and then get the acceleration from there. That would be a great way to combine 2 concepts from 1 unit. Okay, so yeah, vector addition, definitely a big one. What else? We did 2 labs involving these things. That's the only 2 labs we did.
Friction?
That was in Unit 2. We did do a lab on that, and it will be important. Position versus time, velocity versus time graphs. Okay? We actually used velocity versus time graphs in both units. Okay? When we did the Newton lab, we had the velocity versus time graph to get us the acceleration of the cart. Okay? So yeah, definitely something that would be important. I would say probably going to appear on the exam in either the multiple choice and or the written response part. Okay, what else? Something you can get from this graph. Acceleration. Also something that is in more than 1 unit. In fact, it's kind of in all the units. Okay? It's part of Newton's second law. It's part of centripetal force. It's part of energy and Hooke's law in an oscillating object. Okay? It's in every single unit. So that's one of those kind of big overarching concepts. Okay. We used a little bit of this and a little bit of this in this concept that we talked about near the end of that unit. Projectile motion. Okay, I would say those are the biggest things in that unit. Okay, if I was going to study stuff from Unit 1, those would be the 4 things I would spend time on. Okay, now V equals D over T, that's another one that kind of is everywhere, but I don't really think you need to spend a lot of time working on V equals D over T. I'm like abundantly confident in your ability to use that formula. It is part of projectile motion and position versus time graphs. Okay, so if I'm the person writing your test, wait, I am the person writing your test. So, okay, if I'm the person writing your test, and I'm trying to be efficient about how I test things, which one of these concepts could I use to test 2 out of the other 3? Projectile motion tests everything from Unit 1 except graph. it be a good thing for me to put on the final? Here's a big hint for you. Question number 1 in the written response is projectile motion question. Okay. Where you'll be asked to do some v equals d over t, some acceleration, and some vector components, okay? Because that's a great way for me to test whether you can do all of that stuff still. Okay, so expect a projectile motion question. Okay, it is the first question in the written response. And it is very much like all the ones we did in class. Okay, I'm not trying to trick you in any way with that question. Okay, I just want to see if you can still do all the things I taught you. All right. In terms of graphing, definitely expect there to be some of that. Okay, some of it might be more like here's a picture of a graph and a multiple choice, and you have to interpret it. Or there could be some y equals mx plus b in the written response. After all, we had to do that on both of our labs. Okay, so it could be something that comes up. You know, for a velocity versus time graph, you know, getting acceleration or getting displacement from it. Okay, those are things that you were asked to do in the acceleration lab, so it's something I'll probably ask on the final. Okay, it's just not all the little nitpicky things are going to be there. Okay, just the big things. Those are the big things from Unit 1. Okay, definitely those things. Okay, so when we started out Unit 1, we started out with just scalars and vectors. So is that also something that's kind of overarching? Okay, certainly for Unit 1 and Unit 2, vectors were really important. Okay, so definitely know which quantities are vector quantities, which quantities are scalar quantities. Okay, understand how you treat them when you're using them. Okay, that's going to be kind of a big deal as well. Okay, and we talked about v equals d over t that same day, okay, which was kind of review for you. So there could be like some simple v equals d over t scalar vector things in the multiple choice. Okay. Incidentally, there are not a lot of multiple choice questions on your final. Okay, it's 21 multiple choice, 12. Okay. Then right after that, we did position versus time graphs. Okay, that was the second thing we did in the unit, right? So we worked on you know, interpreting what they meant. Okay, then we talked about velocity versus time graphs. Okay, how you interpret them, calculate things from them, and then naturally from there it progressed to acceleration, because acceleration was one of the things you could calculate from the velocity versus time graphs. Okay, and then from there we went to vector addition. Okay, we spent quite a bit of time on vector addition, right? Looking at how we do vector addition questions, vector components, all of that stuff. And then we went to projectile motion after that. Okay, that was the whole unit. And it seemed a lot longer than that, but we were teaching you new skills at the time. Okay, so what I'm going to do today is kind of give you some practice questions that you can try. I'll take questions from you guys on Unit 1 if you have them. Okay, and then we'll just kind of progress through the class and do what you guys need done. Okay, I mean, if you guys don't give me anything, you don't ask any questions, and I just make up what I think you should do. Okay, but that doesn't really help you if you're thinking of something else. Okay, so if there's something, some burning question that you have, okay, or something you'd really like to do again and see done, ask. Okay, that's how the review gets best done. Right? So let's start with that. Let's see how much we remember about adding vectors together. Okay, so we want to add these two displacement vectors to find the total displacement. 10 meters at 38 degrees north of east and 15 meters at 19 degrees south of east. Okay, just in case you're like drawing a complete blank right now. How do we draw vectors? Tail to head. Tail to head. Okay, draw the arrow, X's and Y's, tail to head, the resultant. Okay, I'll give you a few minutes and then I'll put the diagram up there. Okay, so that's your diagram for that one. Should look like tail to head. Okay, we have the 10 meter vector that's 38 degrees, okay, north of east, so slanted upwards. Okay, it has its X component here on the bottom, its Y component here on the side, and then it is put tail to head with the 15 meter vector that is 19 degrees below the X-axis, or south of east in this case. Okay, so there's our X component, there's our Y component, and that means that our resultant goes from start to finish, looks like that red arrow, okay, and has its own x and y components. Okay, anybody done the whole thing already? Okay, I'll give you about another 3-4 minutes, and then I'll start doing the math. All right, so the first thing we got to do is we got to find all the x's and all the y's. Okay, so we'll start with the first vector, which was colored green. Okay, so green x, okay, is going to be the adjacent side, so that'll be the cos of 38 degrees times 10 meters. All right, so we're looking at 7.88 meters east. Okay, the y component is the opposite side, so it'll be the sine of 38 times 10. Okay, so 6.16 meters, and that is north. All right, then we've got to find the x's and y's for the black triangle. So black x is the adjacent side, so cos of 19 times 15 meters. All right, so that side is going to be 14.18 meters, and it is east. Okay, and then the y component is the opposite side, so sine of 19 times 15 meters. All right, so we're looking at 4.88 meters south. Okay, now that we've got those vector components, what do we do with them?
You add the east ones together?
Okay, so I add the x's together, the horizontal ones that are east. Okay, so that'll be my first step. When I do that, I will get red x, okay, or rx, resultant x there. Okay, so rx is going to be then 7.88 plus 14.18. That's supposed to be a plus. 14.18. All right, now I want to have all the decimals in place so that I'm obeying my significant digits here. So that one plus that one. Okay, so that's going to give me 22.06 meters east. All right, then I got to do the same thing with the y components. All right, so for ry, I'm going to have 6.16 meters north. Okay, and I'm going to subtract the 4.88 meters because it's south, or I just add the negative, whichever. I just have to reflect that they're in opposite directions. Okay, I'm going to do that by subtracting. Okay, so I'm going to take that 6.16 right there, and I'm going to subtract the 4.88 right there. Okay, and I'm going to get that my resultant y is very small, 1.27, which fits with the diagram. Meters north. Okay, now I've got the two sides of the red triangle. What do I do next?
A squared plus b squared.
Right, use the Greek geek, okay? Use Pythagoras. Okay, so we are going to go square root of that number squared plus that number squared. Okay, so I get, well, barely more than what I had for the other one because it's such a small side over there. And so that's going to be 22.1 meters. But now I need the vector, okay, and I can get the vector using trig. I can use whichever trig function I want, but I like using my favorite one, which is tan. Okay, so second tan of the opposite side, 1.27, divided by the adjacent side, which was 22.06. Okay, so I get an angle there of 3.3 degrees. Actually, how many significant? I only have two significant digits. So 3.3 degrees north of east. Okay, 22 meters because I only have 2 significant digits. Okay, is that ringing a bell? I mean, we did that back in September. That was a long time ago. Okay, I mean, we did it a little bit in October as well in the second unit, but okay, long time since we learned it. Okay, making some sense? Okay. Nope, that's the second unit. We don't want that. Also second unit. What the heck is going on here? Well, I thought I had more questions on it. Okay, what would you guys like me to go over?
Can you do like a maximum height question?
Oh, for projectiles. Okay, let's do a projectile question, yeah. Okay, so, a ball is thrown. At, let's say 25 meters per second at 25 degrees above the horizontal. Okay. How far I hate that when you got I and E, never looks right, because that whole I over, I before E except after C, except in all these words where that rule doesn't apply, like that one, and weird, and yeah. Okay, try that question. Okay, to get this one started, okay, we have to draw the projected velocity vector, okay, which is 25 meters per second, and I picked a terrible angle, 25 degrees above the horizontal. That projectile is going to do this, it's going to follow an arc, okay, that re-encounters the ground over there. So we're looking for how far it will travel horizontally and what maximum height it will reach, which means it needs to be broken up into its vertical and horizontal components. Okay, what do I have to remember about the vertical component? What kind of motion does it undergo? Acceleration, because of gravity. Okay, so I have to remember that the vertical part of this is going to be affected by that. Okay, what kind of motion does the horizontal part undergo?
Uniform?
Uniform, constant velocity. Okay, there aren't any forces acting on it horizontally. Okay, so we're looking at a V equals D over T situation for the horizontal part. Okay, how many people have it done? Okay, I'll give you some more time on that one. Okay, then we'll have a look at it, but hopefully that helps you if you were a bit stumped. All right, so one of our givens is that acceleration is negative 9.81. Okay, the rest of the stuff we've got to get from vector components. This side is going to be our initial vertical velocity. All right, so I'm going to calculate my initial vertical velocity by going the sine of 25 times 25 because I picked wonderful numbers. Okay, so sine of 25 degrees times 25 meters per second. All right, so we get 10.56 meters per second. positive because it's up. Okay, now, if I'm dealing with the whole flight, launch and impact, and they're level, what's the final velocity? Nope. Right before it hits the ground, what's the velocity vertically? If its initial velocity was positive 10.6. Same but negative. What goes up must come down. Okay? If I throw something straight up in the air, when it comes back to my hand, it's going just as fast as when I threw it. Okay? So that's one of the important things we have to remember about projectile motion in this situation. All right. Horizontally, I need to get the horizontal velocity. Okay, so V horizontal, that's going to be the adjacent side, or the x component of that. All right, so for that I'm going to go cos of 25 times 25 meters per second. .66 meters per second. Okay, I'm trying to find first the horizontal distance traveled. What am I missing? Time. Okay, can I find time with my vertical information? Does basically every projectile motion question require me to find time? Time is important because it can be used for both the vertical and the horizontal parts. Okay, it's the one thing that they share. So I'm going to go time equals VF minus VI over A. So that's going to be negative 10.56 minus 10.56, okay, divided by negative 9.81. Okay, so that means basically taking that number there and multiplying it by 2 and then dividing it by 9.81. Okay, so this ball is in the air for 2.15 seconds. Okay, that number can come over here, 2.15 seconds. All right, D equals V times T if I manipulate that formula. All right, so all I have to do then is go 22.66 times 2.15 seconds, and I will have the horizontal distance traveled. Okay, so to two significant digits, we are looking at 49 meters horizontally. Okay, is that ringing a bell from unit 1? Okay, the other thing we were supposed to find, which is what you asked for, okay, is the maximum height. Is there more than one way to find that? There are actually two ways to find it. Okay? Here's what I have to remember about the maximum height. The maximum height occurs here, exactly halfway through the flight. Okay? So that means that this value that I calculated for time, which is for the whole flight, would have to be what? Cut in half. Okay? That would be one of the ways I could calculate the maximum height, is I could take this time, divide it by 2, and then use this formula. D equals VI times T, because I know what VI is. I divide this number by 2 and I've got my time, plus 1/2 times A, which I know is negative 9.81, times T squared. Okay? That would give me the maximum height. The reason I don't like using that method is people forget to divide the time by 2. Okay? Then they get the wrong answer. So we can do it that way. Okay? We can plug in our numbers here. So we'll go 10.56 times, in brackets, that number there, divided by 2, okay, plus 0.5 times negative 9.81 times, in brackets, that number, divided by 2 squared. Okay, so I get 5.7 meters. using that method. Okay, the other method, the one that I like to use, involves using VF. What's VF vertically at this point? 0. Okay, that's the point where it stops for a second before it starts to fall back down to earth. Okay, so that means that I could use this formula. VF squared equals VI squared plus 2AD. I'd be looking for D here, so I would subtract. So I'd have VF squared minus VI squared divided by 2A would equal D. So for me, that's going to be 0 squared minus 10.56 squared divided by 2 times negative 9.81. Okay, so in brackets 0, because 0 squared is 0, minus that number squared, okay, divided by 2 times negative 9.81. Okay, gee, I get exactly the same number. That's a good sign. I either did it wrong twice or I did it right twice. I did it right twice. Okay. All right. So 5.7 meters. Okay. Either way will work. Okay. Is that what I'm going to ask you on your final? Probably. I don't think I'm going to give you a horizontal one because that doesn't involve you having to do any vector components. Okay. This is the one that it makes you do vector components. Okay. And that's what I want to test on the final. All right. Do you have a whole bunch of practice projectile motion problems in your workbook? Yeah. Do you have the answers for them? Might be a good idea to try to do those. Okay. Plus, in the final exam review package, which we'll post tomorrow after school, there's a couple more. Okay, projectile motion problems that you can try with the answers. Okay. All right. What else do we want to go over from Unit 1? Okay, so velocity versus time graph. I'm just going to make up some numbers here. I'll make it end there. Okay, so it's a velocity versus time graph. What's the object doing here?
Moving at 6 meters per second.
Moving at a velocity of positive 6 meters per second, or moving in a positive direction at 6 meters per second. Absolutely. What's it doing right after that? Well, we could say decelerating, but that implies that at the end it stops. Accelerating in a negative direction, absolutely. Okay, because it actually does change direction. At what time does it change direction? When you change direction, does your velocity go from positive to negative? Okay, so when does that happen?
7 seconds.
7 seconds. Okay, the whole time, this whole section of the graph is a negative acceleration. Okay? During this part of the graph, it looks like the object's slowing down. Okay? And then it doesn't stop. It just goes the other way. Okay? If you were to actually look at an object doing this part of the graph, it would look like if someone ran into a bungee cord. Okay? They're still moving forwards, but they're slowing down. And once they get to the point where they've stretched the bungee cord as far as it will go, they start moving the other way. Okay? It would look weird, but that's what would be going on. That part of the graph is exactly that. It doesn't look like that on the graph, but that's what it would look like in real life. Okay? All right, what's the object doing during this part?
Moving at 3 meters per second in the negative direction.
Yep, moving at 3 meters per second in a negative direction. Okay? And then what's it doing here?
Accelerating in a positive direction.
Accelerating in a positive direction until it
Stops.
stops. Okay. Since you have some numbers there, I would like for you to calculate for me the total displacement of this object. It's not zero. All right, if I'm going to calculate displacement, what I need is average velocity times time, okay? Which on a velocity versus time graph basically means calculating the area between the line and the x-axis. Okay, if it's a square or a rectangle, like this first part, its average velocity is the height of the rectangle, 6 meters per second. And it does that for 5 seconds. Okay, so this area here, okay, is the displacement during that part, 30 meters, 6 times 5. Right? Then, during this part of the graph, it's changing its velocity. So its average velocity is halfway between the top and the bottom, or height over 2. Base times height over 2. Okay, that's still going to be average velocity times time. So the time for this triangle is 2 seconds. Okay, the height of this triangle is 6. So 6 divided by 2 is 3, times 2 is 6. Okay, so we got 6 meters there. Everybody all right with that? Okay, then I've got this little triangle here that's 1 on the base and 3 high. So 1 times 3 is 3, divided by 2 is 1.5 meters, but negative. Okay, and then I've got this box that is 3 seconds on the base and negative 3 high, so it's negative 9 meters. And then this one here is identical to this one. Okay, it's 1 on the base and negative 3 high, so it's also negative 1.5 meters. Right? What do I do with all those numbers? Add them up. Okay, so I got negative 3, negative 12, okay, plus 6, plus 30. Okay, so 36 minus 12 should be 24 meters, positive 24 meters, yeah? If my mental math is right. Okay, did I ask you to do that stuff in Unit 1? Absolutely I did. Okay, so is that something that might show up on a test? Possibly. Okay, as could y equals mx plus b. Okay, one last thing about this graph. What if I asked you to calculate the acceleration between 5 and 8 seconds? Do I have a formula that calculates acceleration? I have many, actually. Okay? On this graph, I can get initial velocity, final velocity, and time. Do I have a formula that uses those 3 things to get acceleration? Is this also going to calculate the slope of this line? It is, because change in velocity divided by time is acceleration. That's what the slope of any line on this graph would represent. Okay, so we're going to have negative 3 minus 6 divided by 3. Okay, so negative 3 minus 6 is negative 9, divided by 3 is negative 3 meters per second squared. Again, if my mental math is correct. Okay. Ringing a bell? I would have asked you to do the same things in Science 10. Okay, that's something that still came up. Right, for us in this unit. Okay, let's say I give you something like this. Okay. What's the velocity of this object? That's a 1-mark question, by the way. 7.2 meters per second. This is a position versus time graph. The rate at which I change position divided by time is velocity. That means it's the slope of the line. Okay, slope of the line on this graph would have to equal velocity because that's what it's showing me. Okay? All right. I would like for you to calculate for me how long it will take this object to reach a position of 200 meters. Time to 200 meters. Give you a few minutes on that one. Okay, what am I solving for if I want to find the time to 200 meters? X, because time is on the x-axis. Okay, so what I have to do is manipulate this equation to solve for x. So that's going to mean subtracting 2.59. Okay, y is 200 meters. So 200 minus 2.59, and then divide by 7.2. Okay, that'll give us the time to 200 meters. So 200 minus 2.59 equals divided by 7.2. Right, we're looking at 27 seconds. Okay, you all right, Carter?
Yep.
Okay, we'll take care of that. Okay, what if I asked you what the position of the object would be after 50 seconds? I'll give you 1 minute to solve that one. Okay, position of the object after 50 seconds. Okay, so in that one we're solving for y, because y is position. Okay, so all we have to do is plug in numbers. 7.2 times 50 seconds plus 2.59 meters, which would be the initial position of the object. Okay, so 7.2 times 50 plus 2.59. Okay. 362.59 meters. We only had 2 significant digits there, I think, so 3.6 times 10 to the 2 meters. Good. Is that the kind of thing I could ask you? It is. Okay, anything else from you guys that you'd like to go over?
The 2 displacement formulas we have, what's the distinction between them? Like when should we use one or the other?
Okay, are you talking about the VFT and the VIT ones?
Yeah.
Okay, so the distinction between them is whether you have VI or VF.
That's it.
Yeah, so, okay, you've got this one. Okay, and then you've also got this one, VFT, but it's minus 1/2 AT squared. So where those 2 formulas come from is if I have a velocity versus time graph, okay, that has this shape, okay, they calculate the area under the line. So this first one actually does it by going, all right, here's VI times T, that calculates the box, okay, and the 1/2 AT squared calculates the triangle above it, and then we add them together. Okay. The other formula calculates this box and then subtracts the similar triangle from it to get the area underneath the line.
Okay.
Okay? Yeah, other questions there, guys? Okay, and I could ask an acceleration problem that asks you to use that. It could come up on a projectile motion question for maximum height, okay, something like that. Okay, I'll make one more up. You guys can try here before class ends. Okay, give that one a try. Okay, so I picked this one because it uses that formula that Tyler asked about. Okay, so what's the initial velocity? So we're looking for VI here, okay, of an object that travels positive 150 meters. So they gave me a displacement there, okay, in 23 seconds, okay, while accelerating at negative 4.5 meters per second squared. Okay, so I'm looking for VI, I have D, I have T, and I have A, okay, which means I would have to use this formula if I want to solve it in one step, which of course I do, okay. So if I'm trying to solve for VI, the first thing I'm going to do is subtract 1/2 AT squared over to the other side. Okay, and then I'm just going to divide both sides by T, and that will leave VI over here by itself. Okay, so I'll take my 150 and I will subtract 0.5 times negative 4.5, the acceleration, times 23 squared divided by 23. And then divide that by 23. All right, so we're looking at that would be positive 58 meters per second. On a test, would you have to write the positive? Yes, because the question asked for velocity. And in the question, you were told the displacement was positive and the acceleration was negative. Therefore, you were given reference vectors and then asked for a vector quantity, so your vector would have to match what was given in the question. Those are little tricks I've played on you before. My bag of tricks does not have very many tricks in it, so expect similar types of tricks. Okay, to be played. They're the ones that see whether you're paying attention or not. Okay? All right. Tomorrow is your test for Unit 4. Bring with you pencil for sure. Okay, a pencil, maybe a pen, okay, calculator, okay, and that's it. Formulas are on the front, so you don't need your formula sheet. Okay. If you guys want to, you can start in lunch hour a little bit, right into nighttime a little bit. I'm fine with that. Okay, if you want to start a little bit early, come on in a little bit early. Okay?